Good afternoon, students. Welcome to the second live session of the course Solar Energy Engineering and Technology. So, in this course or in this live session 2, we will be covering of module 5 to 8. So, let us share my slide and let us discuss the content I have covered in these modules. So primarily these modules 5 through 8 we will be covering. So in module 5 we have discussed standalone photovoltaic system. In module 6 primarily we have discussed about grid connected PV system. In module 7 we discussed fundamentals of flat plate collectors, and in module 8 we have elaborated about liquid flat plate collectors. So in lecture 1 of module 5 we try to understand the different components of a standalone PV system. So primary components are PV module, source controller, battery, inverter, and then we must have some kind of loads, maybe AC load or maybe DC load. And also we have discussed design steps of a standalone PV system, and also we have solved problems. In lecture 2 of module 5, we have provided information about design of PV system. So we have given the steps how a PV system can be designed. Of course, this PV system is standalone in nature, and we have applied the concept in water pumping system. And also we have discussed example to strengthen our understanding. In lecture 1 of module 6, primarily we have covered layout of grid connected PV system, different components of grid connected PV systems, then selection of different equipments, then role of different components for maximization of PV efficiency. So these many informations were discussed in this lecture. So in lecture 2 of module 6 we have primarily discussed about design steps of grid connected PV system. Also, we understood the voltage, current, and power ratings of module and inverter are the three criteria which ensures a proper matching of the system in terms of performance and safety. Sizing of inverter based on the size of array was also discussed, and also we have demonstrated how to design a grid connected PV system. So in lecture 3 of module 6, we have systematically studied the performance analysis of a grid connected PV system. Also, we have discussed the numerical problems to determine all the performance characteristics, like what is the energy yield, what is the specific yield, performance ratio, then capacity utilization factor, and average system efficiency of grid connected PV system. So you can have a look the kind of system we have used in the system for designing a grid connected PV system. In lecture 1 of module 7, we have primarily discussed about the classification of solar collectors, different components of a flat plate collector, then performance analysis of a flat plate collector, then transmissivity estimation based on reflection, refraction and absorption. And also we have studied significance of transmissivity absorptivity product. And finally we have also analyzed the instantaneous efficiency and stagnation temperature and how these two parameters are essential in terms of design of flat plate collector. In lecture 2 of module 7, we have discussed about different modes of heat transfer like conduction, convection, radiation, non-dimensional numbers related to the heat transfer, correlations to estimate heat transfer coefficients. So this knowledge is required when we are dealing with solar thermal system. So in all the system we need to cover or we need to analyze heat transfer. In lecture 1 of module 8, we have primarily discussed about collector losses and loss estimation. So what are the loss coefficients like top loss, bottom loss, side loss, overall loss coefficient, and also we have demonstrated the calculation by using iterative and correlations about this heat transfer analysis. So as far as collector losses are concerned, so this can be very easily demonstrated by considering energy balance on observer plate. So what you can see here, this is a schematic or card view you can say of a flat plate collector. So this is glass cover you can consider, and this is observer plate, and this is the casing. Okay, so solar radiation is penetrated through this glass cover and strikes on the observer plate, right? So after that what happens? We have re-radiation and then convective heat transfer takes place and losses are taking place from the bottom, sides and tops. Okay, so if we are interested to write energy balance equation of this observer plate, so Q is the useful heat gain which is equal to amount of solar radiation received by this observer plate, okay, multiplied by the area and then heat losses, right? So this S is the solar radiation flux received by this observer plate is a function of many parameters, okay, which has already been shown in the lecture videos. And this QL, which is nothing but heat loss from the collector, can be expressed in terms of overall loss coefficients. Okay, so QL is nothing but UL multiplied by AP multiplied by temperature difference of this TPM to the ambient. Okay, so this QL can also be expressed by summing all the losses, right, like top loss, bottom loss and side loss, and these losses can also be expressed in terms of loss coefficients. So that's what it is shown, like this UT, UB, US are top loss coefficient, bottom loss coefficient and then side loss coefficient, and this rate of heat loss from the top, bottom and sides can be expressed what is shown here, and then what finally we can calculate is the overall loss coefficient, which is something like this. UL is equal to UT plus UB plus US. Okay, so what does it mean? Like this overall loss coefficient is a measure of all the losses, and you must know this value of losses should be in the range of 2 to 10 watt per meter square Kelvin, right? So if it is more than that, then your design is not acceptable and it should be in between this range. And in the lecture 2 of module 8, primarily we have discussed energy balance of an observer plate, thermal resistance network, then temperature profile of a flat plate collector, then analysis of collector efficiency factor and collector heat removal factor, then instantaneous efficiency, and then finally we understood the series and parallel connection of collectors and what condition we need to connect the collectors in series and what condition we need to connect the collectors in parallel. Okay. So these analysis were included in the lecture videos. So you can see QU already I have expressed. This is nothing but solar radiation flux received by the observer plate multiplied by area of the plate minus QL. Okay, QL already you know what is QL is the loss or rate of heat loss, and this is overall losses. It includes all the losses like losses from the top, bottom and sides. Okay, then what you can see QU in terms of TPM and here QU in terms of TF, and when we are interested about QU in terms of TFI, then our expression will be something like this, and this expression is known as Hotel-Wheeler-Bliss equation, which is very very important because in other cases it is very difficult to know what is the mean temperature of the plate and what is the fluid temperature. Okay, but if we know the inlet fluid temperature, it is very easy to calculate. So that's how this equation has been derived, and this is very very convenient for solar thermal analysis for calculation of useful heat gain. And also we can define this collector efficiency factor, which is nothing but F. This is defined as the ratio of actual useful heat gain or heat collection rate to the useful heat collection rate, which would occur if the collector and observer plate are at the temperature of TF, which is fluid temperature, and that is the mean fluid temperature. And its value ranges from 0.8 to 0.95. And in case of FR, which is nothing but collector heat removal factor, is defined as the ratio of the actual useful heat collection rate to the useful heat collection rate which would occur if the collector observer plate are at the temperature of TFI everywhere. Okay, so which is known, and its value varies from 0 to 1. Okay, FR can also be calculated by using this expression, which is already expressed. So in the lecture 3 of module 8, primarily we have discussed about the various factors influencing the performance of a flat plate collector, like selective surfaces. So what kind of selective surfaces are used to increase the absorptivity of the solar radiation and reducing the emissivity of the radiation, and what number of cover is optimum for maximum absorption of solar radiation, and what spacing should be maintained, what should be the collector tilt if you are not rotating the device, then what will happen if you are rotating the device, then what angle you need to maintain with respect to the time, and dust on the cover. These are very very important parameters need to be seen. And also we have studied evacuated tube collector. In the lecture 4 of module 8, primarily we have discussed the testing of liquid flat plate collector and application of the collector. Okay, so how we can test? If we have to test a newly purchased flat plate collector, then we need some kind of configuration, like here we have to install the system, then we need flow meter, then bypass valve, pump, then storage tank, electric heater, and then some kind of conditioning of the fluid, right? Because we need to perform the experiments at different TFI and your we can fix the mass flow rate, but we have to sense the values of TFI for different experiments. Okay, so that's how we do the characterization of a flat plate collector. And if we see the applications, there are multiple applications, like indoor swimming pool, then water heating, milk pasteurization, what power generation. Of course, it will be low power generation. Then drying, solar water heater for biogas, and the slurry the drying. So there are multiple applications of flat plate collector. So these were the informations we discussed in these modules. So we will now discuss some of the queries of yours. There are some queries I have already received in this discussion forum. So these are very different kind of queries, like for complex numericals, must I remember all the formulas? These are the questions. So you don't have to worry if we ask some questions of that nature. Then of course we'll provide sufficient information to solve the problem. And one question was something like, for calculation of trigonometric values, will a scientific calculator be provided? So see, this NPTEL team will announce this before the exam, and they may provide on-screen calculator or may allow scientific calculators. So this information should be shared with you before the exam. So and one question was something like, will we be asked theoretical explanation of processes and devices in question answer format? So I think most of the questions will be MCQ. I think no explanation is required in this course. And if some charts are required, then of course we will provide the charts to help you in doing the calculation. And no such questions I have received. And one more questions I got from this online discussion. So someone was asking about the software. So the student wants to know the software available for sun tracking and set calculations. So there are different algorithm based softwares are there. So if you are interested, then you can see it. So I just named 2-3 what I observed from the open source, like TwinCat solar position algorithm library. So that permits the exact calculation of sun angles anywhere in the world with the use of sensors. And also one more platform is there for sun sensor ISSAX, so solar MEMS technologies. So this ISSAX sun sensor measures the incident angle of a sun ray in both the orthogonal axes. And this has got high sensitivity, is rich, is based on the geometrical dimensions of the design. So these kind of things you can browse, and of course for day-to-day analysis we prefer something like Polysan or maybe PV system. So these softwares are there. And there is one question like, is this possible to identify monocrystalline, polycrystalline, and Norvege is saying it. Yes, I think this is already explained in the presentation. Video, this is available in video. This is available already. So you can please refer to the video. Then all the information should be clear to you. One question was something like, is it possible to increase efficiency of solar cell more than non-renewable energy source? So solar cell more than non-renewable energy source. It depends. These questions, no, its validity. I don't think it's a very valid question. So what kind of non-renewable system you are talking about? And then solar cell efficiency, you see, if you see the recent value of energy conversion of solar cell, so it's if you consider say a multi-junction solar cell, it's close to 45. Okay, so it's a very high efficiency. And as you know, how much energy is falling if you talk about the spectrum level. So about 45% energy falls in this no visible range. So and that way it is very efficient. And if you talk about say our conventional power plant, so in Indian context, what we can get its conversion efficiency is less than 40%. Okay, that way cell level efficiency is high here, but when we are talking about system level efficiency, so it is not that much. It's about 15%. Okay, so that percentage. Nonetheless, 15%. Again, there are many things. So in average, you can say 15% efficiency. But what is more interesting is no, you are getting free energy. So running cost is not that much. Only sometimes you need to clean the modules. So you don't have to pay for fuels. Already we have answered one question in the discussion forum. So his question was, I have a question about what is happening in the video at some time. So each video was like about standalone system, and his question is not clear to me. What he is trying to ask, he or she, I don't know. Uh, like solar PV system that produces electrical power to charge banks of batteries during the day for use at night. Standalone small scale PV system employs rechargeable batteries to store energy. Then standalone PV systems are ideal for remote areas where other power sources are either impractical or unavailable to provide power for lighting and other uses. Um, so that means no, if no load is connected, the electric circuit is incomplete, which is known as open circuit condition, right? So his question was saying if no load is connected to the PV system, then what happens? So then it's an open circuit, right? So there is no electricity produced when the panel is disconnected from the load. If you have any question, please ask. In the module 5 to 8, One student was asking about concept and technology of solar energy. Uh, yes. What is the question actually that is missing? So yes, you have to clear your concepts and doubts. Then only you can design a PV system. Yeah, Vidyasagar. Yeah, I think they have no got all the doubts in the presentation file itself. So that's why I think they don't have any question to ask. So Vidyasagar, you are the same guy, right? Who came for internship under this NPTEL? So since no comments or queries are here, so I am closing the live session now. Okay, thank you for watching this live session too of solar energy engineering and technology. Thank you once again.